Well, good morning, everyone. As you said, my name is Tom Carey, and I'm a research scientist at the National Nuclear Laboratory, and I work in the Waste Management Decommissioning Division. But what I'd like to do today is tell you some of the work that we've done in the area of decontamination and understanding contaminated materials. Before I do that, what I'd like to do is just set the scene. So, for the past 60 years, the UK have actually been pioneers in the nuclear energy industry. And actually were the first country to build a commercial reactor that was connected to the grid in 1956 and was opened by Her Majesty the Queen. And since then, we've gone on to produce over 20 more reactors that have produced a base load of electricity to the country reliably. However, these reactors are coming to the end of their lifetime now and need to be decommissioned. But this is no easy task, as the materials these sites are made out of have become contaminated, so the steels, the concretes, etc. And because of this challenge is ahead of us, the NDA have actually predicted it's going to cost 117 billion over 120 years to sort this problem out. But in addition to the reactor sites, we've also got other sites across the UK that were built to support the fuel cycle. The biggest example of this is the Sellafield site up in Cumbria, which is 6 square kilometres in size. And there's a common theme across all these different sites. And what that is that all facilities that are often built, they were built with no decommissioning plan in mind. People that operated these facilities are now coming to the end of their working life and are retiring, so that knowledge that they have is being lost. And the areas that need to be decontaminated are often complex and very hard to access by humans. So what's the drivers behind decontamination? Well, first of all, by doing decontamination, you can reduce the levels of waste, the volumes of waste that we have to manage. This leads on to making a safer environment for the workers and also for the public in this country. And finally, by reducing the volume of waste, we can reduce the cost burden that the UK taxpayer has. So what are NNL doing behind this, though? Well, our strategy is to, first of all, try and get a better understanding of the contaminated materials. And by gaining access to them and working with our academic and industrial partners, we can actually understand the problems we face. And then using this gained knowledge, we can then utilise it, and create informed decontamination solutions for the industry. So what I'd like to do now is start off with sharing with you a case study. So this here is the Huntston cooling pond, and what it was used for. It temporarily received spent fuel from the reactors after a 4 to 5 year period, and was stored temporarily before being moved on to Sellafield reprocessing. This pond is made out of concrete, which is then painted, and is quite common across different nuclear sites. However, as this facility was operated, the radionuclides actually leached from the water into the concrete material during its operational life. Now, this facility has actually gone through a decommissioning process, but we were able to capitalise on this opportunity and remove a core from the sides of the wall, and this was actually taken from the splash zone just above the water level. And through what we decided to do is study this further. So, in collaboration with the University of Manchester, we started off by using a technique called autoradiography. Now, autoradiography, what it tells you is kind of a map of where the contamination is. And what we found is there's 2 key hotspots on the surface of this concrete core. As shown here, on the left-hand side, there's quite a concentrated spot and a high concentration of strontium radionuclides. On the right-hand side, there's more diffuse spot, spread out a spot, and that was due to cesium. Okay, so that's good, and it tells you where they are, but what we want to know is how are these radionuclides bound and how far they penetrated into the wall. So what we did is we took this core down to the diamond light source, and for those of you who don't know what that is, it's a highly impressive facility down in Oxfordshire where you got access to a range of high-resolution techniques to analyse your samples. But the technique we used is X-ray absorption spectroscopy. And what this was able to tell us was how far and what these radionuclides are binding to. So here, what we show is the different layers of paint from A to F that was put onto the walls of the concrete throughout its operational life. I'm not sure who was responsible for layer C, but it may have been a Friday afternoon job. But by studying this core in this way, what we found actually that the strontium radionuclides were binding to the titanium oxide pigment inside the paints. And this kind of information is key to understanding the challenges that we face during decommissioning. There are other findings, but if you want to know more about this particular work, we reported this work in the Journal of Hazardous Materials, and you can find that there. But it's not only concrete we're looking at. When we come to decommissioning, there's a whole lot of other range of materials and orientations we need to sort. So pipes, vessels all need to be decontaminated. Airborne contamination needs to be sorted. And secondary waste that's generated from the decontamination techniques needs to be processed. So the NNL are working on a range of decontamination technologies to sort this problem. But what I'd like to focus on in particular is contaminated stainless steel. And there's a fair amount of it in this country. In fact, actually 32,000 tonnes of intermediate level waste that exists. And this is going to cost approximately 300 million to process and store. But what's been found is that the contamination in stainless steel is actually surface deep. So if you can remove the surface layers of the stainless steel, then you can remove the majority of the contamination, and the bulk of the material can be either recycled or recategorized. And a technique that's used widely in the metal finishing industry is electropickling. And this, as I said before, removes the surface of the stainless steel quite effectively and is often used to remove things like scale and heat tinting. Now, what NNL have been doing in this area is actually working with a small medium enterprise company called CTEC, and they've taken this technology further and developed a methodology actually stripping the surface of stainless steels in a much more efficient way. And in terms of austenitic stainless steel, actually 3 times. So this is all well and good, but they're really looking at effluents that are used in the metal finishing industry, and we wanted to apply it in the nuclear industry. So we've been working alongside with these guys to nuclearise this technology. So approximately 6 months ago, we took some samples of typical grades of stainless steel that are used in the industry, and actually showed you could strip the surface very quickly of the stainless steel using nuclear effluents, and you actually produce a waste product that could potentially be compatible with the waste effluent streams that exist already in the industry. Now, that's all I've really got time to speak to you today, but what I'd like to leave you with is that NNL have got experience in working with hazardous steels and working to produce decontamination technologies. And the drive for this is to make decommissioning faster, cheaper, and safer. Sorry. If you'd like to hear any more about, please come and speak to me on touchscreens, and I'll hopefully speak to you then. Thank you.